imagine that how M, when it produces a test, it might actually have some intuition for why that test is correct. But the symbolic part never gets to use that intuition. And at the same time, the symbolic checker, it'd be nice if it produced some intuition.
Good, okay. Okay, so why is this a limitation? It's a limitation because I would argue that in a certain sense, every piece of data is neurosymbolic. So if we look at the string password123, we have its sort of logical interpretation as a particular sequence of characters. But then we also know this is a poor password choice, which is sort of a learned connotation that we might have. And my argument is that ultimately what we want are neurosymbolic reasoning systems that can hold these two interpretations simultaneously, where connotations can guide logical reasoning for scalability reasons, and then the act of logical reasoning can actually update the connotations associated with data and computation. To achieve these, I believe that we need new computational models and then new programming languages built on top of these models. So I'm advocating for sort of abandoning the sequential Nessie architecture in favor of something that's more like a parallel neurosymbolic architecture, where you have as input a symbolic program equipped with intuition about that problem. And then you have computation over symbols and intuition in parallel, producing a symbolic conclusion equipped with intuition for that conclusion. So this is sort of the high-level conception for what I'd like to achieve. And my initial solution for this is the Neurosymbolic Transition System. So this is a new computational model consisting of 3 ingredients. The first is a traditional transition system. So you can think about like an abstract machine for a programming language, or a small step operational semantics. So it's something consisting of states and transitions. And an important thing to note is that you can have non-determinism where a single state can step to multiple target states. The second ingredient is going to be a domain of intuition that's equipped with 2 operators, one for combining 2 pieces of intuition and another for making inference over intuition. So for a simple example, your domain of intuition could be text, combination could be concatenation, and inference could be prompting an LLM with that text. And then the third ingredient is you're going to need to be able to assign intuition to initial states and every transition in the system. So we have our initial state S1. We can going to have to give it some initial intuition I1. And then for each of our transitions, we'll also need to assign some intuition to that transition. And then what's going to happen is during runtime, this neurosymbolic transition system is going to step symbolically and intuitively in lockstep. So we have our initial state with some initial intuition. we can step to a new state just following the symbolic transition system, and then create a new intuition at that state by using this combine operator applied to our initial intuition and then the intuition for that transition that's been taken. We can do that again. Here we get to sort of an interesting state because there's a decision that needs to be made. Do we go to state S5 or do we go to state S4? And here we can query the intuition that we've generated via the infer operator to get a kind of like a hint about which state to go to. And now we've reached the end of our computation, and we have some intuition I4 associated with our final state, which is going to be the intuition for the conclusion we've reached. So what are the properties of this type of system? Well, the cool thing is that every step taken by the neurosymbolic transition system could also be taken by the underlying transition system, which means that we can more easily construct computations with good properties by reasoning about that underlying transition system. And despite the fact that you have this strong symbolic backing, you can still take advantage of the generative abilities of LLMs. And to argue that, I'd say that these three scenarios are kind of roughly equivalent in terms of expressivity. You have an LLM guessing a solution is about equivalent to a transition system, which is a non-deterministic grammar that generates a candidate solution. And then in the model I'm proposing, the NSTS, we'd have a non-deterministic grammar that's guided by the LLM to help choose the productions that are used in that non-deterministic generating candidate solution. So I won't go into the details here, but ultimately the hope is that we can take this computational model and then actually use it to construct programming languages. And in the paper, I have a kind of a sketch about how you might be able to do this for logic programming. But the gist of it is that you'd be able to write LLM-powered enumerative program synthesis using code something like this, where ultimately you want to create a solution. You do so by generating a term according to a non-deterministic grammar, and then you verify that that term meets some specification according to this verifies predicate, which I haven't defined here. And what is happening behind the scenes is that the LLM guesses a derivation for this solution predicate query. Then logic programming search is biased by that guess derivation. As the logic programming search progresses, you have this intuition state, which is updated by the steps that the abstract machine is taking. And then when you make a conclusion in logic programming search that violates an assumption made by the LLM in its guess, then you query the LLM again with that new intuition as a counterexample to the guess it gave before. And so how is this different than what would be happening with the sequential NSE architecture? Well, two main differences are that checking the solution, so the verifies predicate, uses and produces intuition now. So we have intuition kind of running throughout the whole symbolic computation. And finally, if we design our language so that like search is fair overall, it makes it easy for programmers to write stuff like semi-decision procedures, computations that have good properties. So in conclusion, I've advocated for neurosymbolic transition systems as a principled computational model for LLM-powered automated reasoning. I've argued against sequential NSE architecture in favor of something that is at least conceptually parallel. In future work, I want to formalize this computational model, try to build programming languages on top of it, and then apply those programming languages to automated reasoning problems. And I would say I'm looking for both collaborators and students. So if this piques anyone's interest, please talk to me. And thank you.
Hi. Thank you, Aaron. Anyone wants to ask a question can take this microphone.
So I'm trying to understand the difference between the the current state of affairs and what you're proposing. And it seems to boil down to externalizing what you call intuition. Like in your paper, figure 3b, you have a prompt for updating intuition. So you have an LLM writing that prompt and then and then processing it.
Yeah, so in that case, so this is sort of more of a detail of how the language could be implemented, but the prompt would be written by the language designer. Yeah, and so it's the language designer would essentially be handling all the interactions with the LLM, but they'd be starting by taking like an abstract machine for an existing language, like a logic programming language, and then building hooks into it for this LLM interaction is the...
Yes, because the prompt for updating intuition is written in a very natural language style.
Yeah, exactly. Yeah, so...
kind of confused where that came from.
Yeah.
The next question.
Yes. Hi. I really wonder how is the infer function designed, because I didn't check your paper. Is it that all the previous states together with the intuition will be part of the context, or you only put the latest state?
Yeah, so that's sort of an empirical question that I haven't answered yet. So like this is all vaporware right now. Like it doesn't actually exist.
Okay.
So I think we'll have to see what works in practice.
Yeah, sure. And have you thought of like applying this to like proof search? Because it feels to me it's feels really reasonable that because each state would be a tactic state, and you'll have an intuition for each proof state and an intuition for each tactic you take.
Yeah, it seems like a natural fit.
Yeah.
That's a good idea.
Yeah, sure.
Yeah.
Thank you. Thank you for the talk.
Yeah.
Okay, the last question. the last one. Yeah.
Thanks for the super interesting talk. I'm sort of curious, is like the intuition here that the intuition here that the intuition helps guide the search such that you are more efficient than doing something more naive and brute force?
Yeah, exactly. Yeah, because you think about the transition system has a lot of non-determinism in it. And so the LM would help resolve like how you choose that, make those non-deterministic choices.
Gotcha, okay. Thank you.
Yep.
Okay. Thank you, Aaron. It's a very nice talk and very interesting work. Yeah. Okay.